Hello, in this video we'll be working through Unit 4 homework problems 40 through 43, and these problems deal with finding absolute extrema or global extrema. Number 40 asks us to find the extreme values of the function on the given interval and tell where they occur. So we have function f of x equals 1 over x plus ln x, and we want to find the absolute maximum and absolute minimum on the interval between x equals 1/2 and x equals 4. So we are going to begin by finding the critical values of f. So I need to know what is the derivative of f. F prime of x equals the derivative of 1 over x is negative 1 over x squared, plus derivative of ln x is 1 over x. Now I want to know, where does this equal 0, or where is it undefined? So I can tell just by looking at it that it's going to be undefined when x is 0. But we also want to know, where does f prime of x equal 0? So I'm going to get a common denominator. I'm going to multiply the second fraction by x over x. And then I have negative 1 plus x, or x minus 1, over x squared is the equation of f prime of x. This is equal to 0 when x is 1, and it's undefined when x is 0. So we have critical values of f at x equals 0 and 1. Now we can make a first derivative sign chart, place our critical values on our number line. But in this problem, we're working on a closed interval. So we should also put our endpoints on our number line, and we can ignore all values outside of our endpoints. So on the right, we have x is less than or equal to 4. On the left, we have x is greater than or equal to 0.5. Well, 0.5 is here, which means I can now ignore all values that are less than 1/2. So I don't even really need to consider that other critical value of x equals 0. And now we're testing our first derivative to see whether it's positive or negative. So I'm going to pick test points. I need it somewhere between 1/2 and 1. Let's just go with 3/4. So 3/4 minus 1, that's negative, and 3/4 squared is positive. Negative over positive is negative. So I know my function f is decreasing on this subinterval. And then a test point between 1 and 4, we can pick 3. 3 minus 1 is positive. 3 squared is positive. Positive over positive is positive. So my function f is increasing on this subinterval between 1 and 4. And that tells me that I have a relative min when x is 1. Now, sometimes we don't know if our relative min is also our absolute min. In this problem, we can conclude that it is, because our function is decreasing and it hits this one turning point and then starts increasing. So this has to be the lowest point because there are no other turning points in our interval. So I know that x equals 1 is my absolute minimum. I don't know my absolute maximum without checking the y-coordinates of my endpoints. Typically, we would check the y-coordinates of all the relative extrema and the endpoints and then conclude what our absolute max and min are from there. So I'm going to go ahead and do that, since that's the process we'll normally be following. So I would find f of 1, and then I would find f of 1/2, my left endpoint, and f of 4, my right endpoint. F of 1, I'm looking back at my original function, is 1 over 1 plus the natural log of 1. The natural log of 1 is 0, so this is just 1. F of 1/2, I have 1 over 1/2, which is 2, plus the natural log of 1/2. And that is approximately 1.307. F of 4, we have 1 over 4 plus the natural log of 4, and that is approximately 1.636. Okay, so the lowest value here is the 1, so that's my absolute minimum at x equals 1. The absolute minimum value is 1, my y-coordinate. And from this list, the highest value is the 1.636. So my absolute maximum occurs at x equals 4, and that maximum value is 1.636. So you do have to pay attention to how the question is worded. to know whether you're supposed to be giving the x-coordinate or the y-coordinate. The extreme value, the extreme minimum value, so we'll just say the absolute min value is 1. And here, the absolute maximum value is 1.636. Part B, g of x equals e to the negative x, and we're working on the interval from -1 to 1. So we want to take our derivative and then find our critical values. Derivative of e to the negative x is e to the negative x times -1. We're going to set that equal to 0 to find our critical values. We can divide both sides by -1, and then we have e to the negative x equals 0. We can rewrite that as 1 over e to the x equals 0, and this has no solution. E to the x is always positive. E to the negative x is also always positive. So there are no values of x that are going to make this equal 0, which just means we have no critical values on our interval. We can still make a first derivative sign chart, and we're working on the interval from -1 to +1. It's not very interesting because we only have the one subinterval, but we can pick a test point. Let's just use 0. That's between -1 and 1, our endpoints. If we put 0 into our first derivative, we get 1. And here's our first derivative equation. When x is 0, we get negative e to the 0, or -1. So our derivative is negative, and that tells me that my function g is decreasing. So strictly decreasing on our interval. Now we're going to look at the y-coordinates. We don't have any critical points to check y-coordinates there, but we can get our endpoints. So g of -1 and g of +1. I'm going to the original equation, which is just e to the negative x. So g of -1 is e to the -1, or e to the 1, or just e, which is approximately 2.72. And then g of 1 would be e to the -1, or 1 over e, which is approximately 0.368. So our highest value is here. That's where we have our absolute max. Our lowest value is here. That's where we have our absolute min. Okay, so we can say g of x has a maximum value of e and a minimum value of 1 over e on the interval from -1 to 1. We're also asked where they occur. So to answer that part of the question, we would say g has an absolute max at x equals -1, and g has an absolute min at x equals +1. Part C, h of x equals natural log of x plus 1, and we're working on the interval from 0 to 3. So we'll find our derivative, h prime equals 1 over x plus 1 times the derivative of x plus 1, which is just 1. So we have critical value for h at x equals -1. -1 is not in our interval. So when we make our sign chart, we're just going to go from 0 to 3, and there are no critical values in that interval. We'll pick a test point of +1, and when I put that back into h prime, I get positive, which tells me that my function h is increasing on our interval. Now, it's kind of obvious if the function is strictly increasing that our absolute min is going to be on the left side and our absolute max is going to be on the right side. But we can verify that by finding the y-coordinates at each of those endpoints. I want h of 0 and h of 3. h of 0 is going to be the natural log of 1. We're going back to the original equation for h. So that's just equal to 0. h of 3 is natural log of 4, which is approximately 1.386. Okay, so the absolute minimum value of h of x is 0, and the absolute maximum value of h of x is ln 4 on the interval from 1 to 3. If we extended that interval, our answers to that would change. Now to say where they occur, I can say that, let's say, h of x has an absolute min at x equals 0 and an absolute max at x equals 3, again on the interval from 1 to 3. Part D, k of x equals e to the negative x squared. Now this time we're working on the interval from negative infinity to infinity, so no endpoints. K prime of x equals e to the negative x squared times the derivative of negative x squared, which is negative 2x. Now to find critical values, I wanted to set that equal to 0, and then set each factor equal to 0. E to the negative x squared will never equal 0. Negative 2x will equal 0 when x is 0. So our only critical value for k occurs at x equals 0. And then endpoints are just negative infinity to infinity. I'm going to pick test points and substitute them into my first derivative. So if I pick a test point of negative 100, negative 2 times negative 100 is positive. E to the negative 100 squared is positive. So positive on the left. If I use 100 as a test point, negative 2 times 100 is negative. E to the negative 100 squared is positive. Negative times positive is negative. So k prime changing from positive to negative means k is changing from increasing to decreasing. So we have a relative max at x equals 0, since the value of the derivative at 0 is 0, and the derivative is changing from positive to negative. From this line chart, I can conclude that this relative max is also the absolute max, because there are no other turning points. So I know x equals 0 is the absolute maximum value. And I also conclude that there is no absolute minimum value. Since we're working on the interval from negative infinity to infinity, and after x equals 0, the function is strictly decreasing, that means we have no absolute minimum value. So k has an absolute maximum value of 0 at x equals 0. So I was able to put both of those answers in there in that one phrase. And no absolute minimum. Part E, f of x equals the sine of x plus pi over 4. We're working on the interval from 0 to 7 pi over 4. So let's find our derivative. F prime of x equals cosine of x plus pi over 4 times the derivative of x plus pi over 4, which is just 1. Now to find my critical values, I want to know where is this equal to 0. Cosine of stuff equals 0. Well, I know cosine is 0 at pi over 2, so the stuff is equal to pi over 2 or 3 pi over 2. And I'm only working on the interval from 0 to 7 pi over 4, so I don't need to find any other solutions besides these two. Now solving for x, we're going to subtract pi over 4. So that gives me x equals pi over 2 minus pi over 4. Pi over 2 I can think of if we get a common denominator here, and we can do the same thing over here. So that's 2 pi over 4 minus pi over 4 is just 1 pi over 4. And then over here I have 6 pi over 4 minus 1 pi over 4 is 5 pi over 4. So those are my two critical values that I'm working with on this interval. Pi over 4, 5 pi over 4. And then I have my endpoints, 7 pi over 4 and 0. So I'm going to choose some test points. Between 0 and pi over 4, we can go with pi over 6. Now remember, we only need to know if the derivative is positive or negative. So let's think about the unit circle. My test point right now is pi over 6. So when I substitute that back into my derivative equation, I want to know what is the cosine of pi over 6 plus pi over 4. Well, pi over 4 is here, and if I add pi over 6 to that, it takes me somewhere over here. And the cosine, since I'm still on the right side of the y-axis, the cosine is positive. Now let's pick a test point between pi over 4 and 5 pi over 4. Let's just go with pi over 2, because pi over 4 is right here. 5 pi over 4 is here. So I'm going to use pi over 2 as my test point. Going back to the f prime equation, I need the cosine of pi over 2 plus pi over 4. So pi over 2 plus another pi over 4 is going to end up right here. And the cosine here is negative since I'm on the left side of the y-axis. So cosine negative. Now I need a test point between 5 pi over 4 and 7 pi over 4. Well, 5 pi over 4 is here. 7 pi over 4 is here. So let's use 3 pi over 2 as our test point. Putting that back into my derivative equation, I get cosine of 3 pi over 2 plus pi over 4. So 3 pi over 2 is here. Add another pi over 4. That takes me right here. And the cosine is positive since I'm on the right side of the y-axis. So my function f is increasing, decreasing, increasing. So we have relative max at pi over 4. We have a relative min at 5 pi over 4. And since we're working on a closed interval, we have endpoints of 0 and 7 pi over 4. Now we really don't know if these relative extrema are the absolute extrema or if one of the endpoints is going to be the absolute extreme value. So we have to check. We go back to our original equation and we evaluate our relative max and mins. So f of pi over 4 and f of 5 pi over 4. And then I also want to check my endpoints, f of 0 and then f of 7 pi over 4. At pi over 4, we're going back to the original function. I want the sine of pi over 4 plus pi over 4. Pi over 4 plus pi over 4 is 2 pi over 4 or pi over 2. So sine of pi over 2, and that's equal to 1. When x is 5 pi over 4, I want the sine of 5 pi over 4 plus pi over 4. That's 6 pi over 4, which reduces to 3 pi over 2, and that is equal to negative 1. At 0, we want the sine of pi over 4, which is 1 over root 2. And at 7 pi over 4, we want the sine of 7 pi over 4 plus pi over 4 is 8 pi over 4, which is 2 pi, and the sine of 2 pi is 0. So here's our absolute minimum value of negative 1 that occurs when x is 5 pi over 4. And of these values, the highest one on the list is 1. So that is going to be our absolute max. This one was our absolute min. So f has an absolute min value of negative 1 at x equals 5 pi over 4. And f has an absolute max value of 1 at x equals pi over 4. And part F, g of x equals secant x, when we're working on the interval from negative pi over 2 to 3 pi over 2. We start by taking our derivative. The derivative of secant x is secant x tangent x. And it may be easier if we're not using a calculator to write this in terms of sines and cosines so we can get our critical values. So the secant is 1 over cosine x, and the tangent of x is sine x over cosine x. That puts another cosine in the denominator. So now we have sine x over cosine squared x. This is going to equal 0 wherever the numerator is 0. So we have critical values when x is, and remember we're working on the interval from negative pi over 2 to 3 pi over 2. So negative pi over 2 all the way around to 3 pi over 2. Sine is 0 at 0 and at pi, and then 2 pi is outside of our interval. So just those two places. Now where is it undefined? The derivative is undefined where cosine is 0. So that's going to be at negative pi over 2, at pi over 2, and at 3 pi over 2. I'm going to place my critical values on a number line. So our smallest is negative pi over 2, which also happens to be our endpoint. And then 0, pi over 2, pi, and 3 pi over 2, which is our other endpoint. So we're going to test g prime to see whether it's positive or negative. We need a test point between negative pi over 2 and 0. So let's go with this one right here, negative pi over 4. And I'm looking at my derivative equation, and I know my sines and cosines better than my secants and tangents. So, but remember, we just need to know positive or negative. We don't really need to know what the values are, just positive or negative. So my test point is negative pi over 4. I'm in quadrant 4. The sign is negative, and the denominator is squared, so that's going to be positive. Let me go ahead and mark where we're 0 and where we're undefined. So derivative was 0 at 0 and at pi, and the derivative was undefined at these other 3 critical values. Okay, so back to negative pi over 4, quadrant 4, sine is negative, cosine squared is positive, so this is going to be negative. Now a test point between 0 and pi over 2, we can use pi over 4. So here sine is positive, denominator is positive, so positive. A test point between pi over 2 and pi, we can go with this one right here. The sine is going to be positive because we're above the y-axis. Cosine squared is positive. So another plus. And then between pi and 3 pi over 2, we can use this angle right here. We're in quadrant 3. Sine is negative since we're below the y-axis. Sine is negative, and the cosine is positive, so that's going to make that negative. So my function g is decreasing, increasing, still increasing, decreasing. We have a relative min when x is 0. The function is undefined at pi over 2, so we have nothing there, and we don't have a sign change there. And we have a relative max when x is pi. So it's unclear whether the relative extrema are also the absolute extrema or whether the endpoints are going to be the absolute extrema. We are going to have to check all of these. So we're going to find g of 0, since that's a relative min, g of pi, since that's a relative max, and then our endpoints, g of negative pi over 2 and g of 3 pi over 2. we're going back to our original equation. Secant x, if it's easier, we can think of that as 1 over cosine x. Let me write that over here. G of x equals 1 over cosine x. And now we're going to substitute 0 in for x. The cosine of 0 is 1, so this is just 1. At pi, the cosine of pi is -1, so this is -1. At negative pi over 2, cosine is 0, so this is undefined. And at 3 pi over 2, cosine is equal to 0, so this is also undefined. So let's think about what's happening here. At these endpoints, we actually have asymptotes. If you remember what the graph of secant x looks like, okay, at negative pi over 2, we have an asymptote. And at pi over 2, we have an asymptote. And then at 3 pi over 2, we have an asymptote. And then our graph looks something like this. So we have a relative min here, but it's not the absolute min because there are other places on the graph lower than this point. We have a relative max here, but that is not the absolute max on this interval. There are other points that are higher than this point. If we didn't have an asymptote at the endpoints, then that asymptote, then the endpoint would probably have been our absolute max, but there is no point at that endpoint on the graph. This just continues to go up, approach along that asymptote. And then on this side, this one just continues to go down along that asymptote. So we have no absolute max and no absolute min. So that can happen when you're working on an open interval or if your function is not continuous on the interval that you're working on. Number 41, for each family of functions that depends on one or more parameters, determine the x-coordinates of the function's absolute maximum and absolute minimum on the given interval. So for part A, our function p of x is 1/3 x cubed minus a squared x. We're working on the interval from 0 to square root of 2 times a. And a is positive. Let's start by finding the derivative of p of x. So p prime equals 3 times 1/3 times x to the power 2 minus a squared. To find our critical values, we're going to set that equal to 0 and solve. So that's x plus a times x minus a equals 0. And that gives us critical values for p at x equals negative a and x equals positive a. So we can make a number line, but our left endpoint is 0. And so we're not going to put negative, and a is positive, so negative a is definitely negative. So we're not going to include the negative a. We can put a, that's a critical value, on our number line, and then our right endpoint is square root of 2 times a, which is larger than a. Square root of 2 times a. We want to test p prime. So I'm going to use the factored form of the equation to see if p prime is positive or negative. A test point between 0 and a could be 1/2 a. So 1/2 a plus a is positive, and then 1/2 a minus a, that's negative 1/2 a, so that's negative. A positive times a negative is a negative. Now we need a test point between a and square root of 2 times a. The square root of 2 is a little bit more than 1.4, so let's just go with like 1.1 times a. So we substitute that back in. 1.1a plus a, that's positive. 1.1a minus a, that's also positive. Positive times positive is positive. So our function p is decreasing until we get to x equals a, and then it turns and it's increasing after that, which tells me I have a relative min at x equals a. It also tells me that that has to be the absolute min because that is the only turning point on this interval. So I've already found my absolute minimum. That occurs at x equals a. But what about the absolute maximum? It's going to be one of these endpoints. So we're going to go back to our original equation for p, and substitute in those endpoint values and see which one is larger. P of 0, I'm looking at my equation for P of x here. P of 0 is 0 minus 0, or 0. P of the square root of 2 times a, well, that's 1/3 square root of 2 times a cubed minus a squared times the square root of 2 times a. So square root of 2 cubed is 2 root 2. So 2 root 2 over 3a cubed minus square root of 2a cubed. If we get a common denominator here, 2 root 2 minus 3 root 2 is negative 1 root 2. So negative root 2 over 3a cubed. And since a is positive, I know negative root 2 over 3 times a cubed is negative. And a negative value is going to be smaller than 0. So this is going to be lower than P of 0. So now P of 0 I know is my absolute max. So we have an absolute min at x equals a, and we have an absolute max at x equals 0. Part B, w equals a minus e to the negative bx. We're working on the interval from b to 3b. A and b are both positive. Our derivative, w prime of x, equals derivative of a is 0 minus derivative of e to the negative bx is e to the negative bx times the derivative of negative bx, which is positive, or which is negative b. So multiplying by negative b, we get positive b e to the negative bx for our derivative. B is a constant. So in terms of critical values, we want to know what value of x would make this whole thing 0. Well, there's no value of x that's going to make e to the negative bx 0. E to the negative bx is strictly positive, and b is positive. So this whole thing is always positive. So if we were to do a sign chart for w prime on our interval from b to 3b with no critical values in between, and knowing that the derivative is always positive, that tells us that w is always increasing. So the absolute minimum has to be the left endpoint, and the absolute maximum has to be the right endpoint. So w has an absolute min at x equals b and an absolute max at x equals 3b. Part C, S equals the sine of kx on the interval from pi over 3k to 5 pi over 6k. S prime of x, the derivative of sine is cosine, so cosine of kx times the derivative of kx, which would be k, and k is positive. To find the critical values, we want to know where does k times the cosine of kx equal 0, or where is it undefined? It's not undefined anywhere, so just where is it equal to 0? Well, we can divide both sides by k, and that gets rid of that guy. And then cosine is 0 at multiples of pi, well, pi over 2 plus multiples of pi. So that means that kx would equal pi over 2 or 3 pi over 2. And then plus multiples of pi from that. So plus pi, I'm not going to use k because we already have a k in this problem, so we'll just say n for some integer n. Now solving for x, we would divide everything by k, so that gives us x equals pi over 2k or 3 pi over 2k plus pi over kn. Now the interval we're given has 3k and 6k in the denominator. So if we write this in terms of 3k, or in terms of 6k, I'd multiply this by 3 over 3. I'd multiply this by 3 over 3. I'd multiply this one by 6 over 6. So that's going to give us 3 pi over 6k, or 9 pi over 6k, plus 6 pi over 6k times n. So now we can see that the 3 pi over 6k is inside of our interval because it's between, well, think of pi over 3k, if we multiply by 2 over 2, as 2 pi over 6k. So 3 pi over 6k is in between 2 pi over 6k and 5 pi over 6k, so that's in our interval. But 9 pi over 6k is bigger than 5 pi over 6k, so that is outside of our interval. And then we can take 3 pi over 6k and we can add 6 pi over 6k to it, but then it'll be outside of our interval. Or we can subtract 6 pi over 6k, but then it will also be outside of our interval. So we don't have to worry about that. This is our only critical value in our given interval. So we have an endpoint at 2 pi over 6k, and our other endpoint at 5 pi over 6k. And then we have our critical value somewhere in between at 3 pi over 6k. And we want to know if S prime is positive or negative on these subintervals. So we need a test point. Let's do the right one first. It looks like it might be a little easier. We need a test point between 3 pi over 6k and 5 pi over 6k. So let's use 4 pi over 6k. S prime at 4 pi over 6k equals k, which is positive, times the cosine of k times 4 pi over 6k. So in that case, the k's cancel out. 4 pi over 6 is 2 pi over 3. Okay, 2 pi over 3 is over here. Well, more like up here. But it's in quadrant 2 and their cosine is negative, so negative. Now, picking a test point between 2 pi over 6k and 3 pi over 6k, we can go with 2.5 pi over 6k. I mean, that's not ideal, but I think we can make it work. Let's go with 2.5 pi over 6k. So again, that's k, which is positive. And then the cosine of k times 2.5 pi over 6k. K's cancel out. So 2.5 pi over 6k is going to be somewhere between 2 pi over 6 and 3 pi over 6. So the 2 pi over 6 is pi over 3. That's here. And the 3 pi over 6 would be pi over 2, which is here. And we know our test point is in between there, which puts it in quadrant 1, which makes the cosine positive. So this is going to be positive. So S is increasing, and then it is decreasing, which tells us we have a relative max here at 3 pi over 6k. And it also has to be our absolute max. It has to be the absolute max because it's the only turning point on that interval. Now, in terms of the absolute min, it could be either one of our endpoints. We're going to have to check both. So let me change colors here, and now we're going to actually check our endpoints. So I need to go to the original equation and find S of 2 pi over 6k. And then I need to find S of the other endpoint, 5 pi over 6k. So in the original function, we have the sine of k times x. So the multiplying by k, multiplying x by k is going to make the k's cancel out. So we really just have the sine of 2 pi over 6, which is the same as the sine of pi over 3. And that is positive square root of 3 over 2. And then here we have the sign of 5 pi over 6k times k, so just the sign of 5 pi over 6. The sign of pi over 6 is 1/2. The sign of 5 pi over 6 is also equal to 1/2. So which one is smaller, root 3 over 2 or 1/2? 1/2 is smaller. So that's going to be my absolute min. And then we already said 3 pi over 6k gives us our absolute max. And we're not asked for the y values, but we might as well go ahead and find them. That would be the sign of 3 pi over 6, which is the same as pi over 2, or 1. So that's going to be our absolute max. So S has an absolute max at x equals 3 pi over 6k and an absolute min at x equals 5 pi over 6k. Number 42, for each of the functions, and we're told each one is continuous on the interval from a to b, state the location of the absolute maximum and absolute minimum on that interval from a to b, or say there's not enough information to make a conclusion. And we're going to assume that any critical values mentioned in the problem represent all of the critical values in that interval. In each case, write one sentence to explain your answer. So part A, all we're told is that f prime of x is less than or equal to 0 for all x in the interval from a to b. So here's our interval, starts at a, ends at b, and we know that f prime is either negative or 0. So it's never positive. So I know my function isn't increasing. It's not increasing. It's either decreasing or staying the same. That means my left endpoint has to be represent the maximum value of the function. But just knowing that the derivative is less than or equal to 0 really doesn't help us find an absolute minimum. Because f could potentially not ever equal 0 on this interval from a to b, or it could equal 0 100 times. Even if we do have some places where it's 0, though, we're never going to get sign changes. So let's just put some zeros on here, and let's just suppose those are all of the zeros. If they're not, we can put some more. But in between all of those zeros, our sign is going to be negative. No matter how many zeros I put on here, in between all of the zeros, the derivative is negative. It's never positive. So my function is just going to be decreasing and then potentially like flatten out and then continue decreasing, flatten out a little bit, continue decreasing. So we know the left endpoint represents the absolute maximum, but not entirely sure about the right endpoint. The right endpoint could be the absolute minimum, or we could have a situation here where the graph of f is just constant. So maybe the graph of f just looks like this. It's just a horizontal line. And then our absolute minimum value occurs at every point inside of that interval. So we don't have quite enough information to say for sure where the absolute minimum occurs, but we know the absolute maximum is going to occur at A. So f has an absolute max at x equals A. And again, if it's this weird situation like we have down here where it's a constant function, then that absolute max occurs at every point in the interval. But we know for sure it occurs at A. And I guess by that line of reasoning, we know it also occurs at B. B might not be the only place where an absolute min occurs. Part B, G has a critical value at C, and C is somewhere between A and B. So we have our endpoints at A and B. C is somewhere in between, and that is a critical value such that G prime of X is greater than 0 for X greater than C, and G prime is less than 0 for X greater than C. That's got to be a typo. It can't be less than and it can't be positive and negative for x greater than. Let's make this a less than. Otherwise, the problem doesn't make sense. So g prime of x is less than 0 for x less than c. Now, at c, the problem here is at c, it didn't tell us if g prime is 0 or undefined, and that's important because our function is decreasing until we hit c, and then it's increasing. If the derivative of g at c is 0, then this is definitely a relative min, and it's also an absolute min because it's the only turning point there. However, if our derivative is undefined at c, then this can't be a relative or an absolute min. It's probably an asymptote or some other kind of discontinuity. So we really don't have enough information to say for sure whether c is an absolute min or not. It's possible that we have an asymptote here, in which case our graph would just continue to go down and there would be no absolute min. Now for the absolute max, it's either going to occur at a and b, since we are working on a closed interval. We have points at a and at b, but we don't know which one is larger, f of or g of a or g of b. So we don't have enough information to determine where the absolute maximum value occurs. There is one, but we don't know where. Part C, h of a equals h of b, and h double prime of x is less than 0 for all x in the interval from a to b. Okay, well, instead of a sign chart, let's just think about the graph. So we have endpoints at a and b, and it tells us that h of a is equal to h of b. So they have the same y coordinate. Okay, my graph, that's super crooked. Let's try that again. Y-axis, x-axis, a, b. We're told that h of a is equal to h of b, and h double prime of x is less than 0. So the second derivative is negative. That means h is concave down. So I know the graph doesn't go straight across. It's got to be concave down the whole time. So for it to be concave down and to reach back to point B, it has to have a turning point in there somewhere. It doesn't necessarily have to look the way I drew it. You know, it could, maybe it goes up here, something like that, and then comes down like that. But somewhere there has to be a turning point. So there will definitely be an absolute max that is in between A and B. A can't be the absolute max, because the only way for A to be the absolute max would be if the graph goes just straight across to B. And that can't be true, because then the second derivative would not be negative. So we know there's an absolute maximum somewhere between A and B, but we don't know where. And we know there's an absolute minimum at A and at B. They have the same y coordinate, so they're both considered the absolute minimums. Okay, so absolute min at x equals A and x equals B. We don't know the value, the absolute minimum value, but whatever it is at A, it's the same thing at B. Part D, P of A is greater than 0, so it's positive. P of B is less than 0, so it's negative. And for the critical value C, such that C is between A and B, strictly between A and B, P prime is negative when x is less than C, and P prime is positive when x is greater than C. So if we do a sign chart and we put our critical value somewhere between the endpoints A and B, P prime is less than 0 when x is less than C, so negative here, and P prime is greater than 0 when x is greater than C, so P prime is positive here. That tells me that P is decreasing until we hit C, and then it's increasing. And we were also told that P of A is positive and P of B is negative, so the endpoint here, the y-coordinate of the endpoint, P of A, is positive, P of B is negative, and positive numbers are higher up on the graph than negative numbers. So P of A is higher than P of B. And over here we can say P of B is lower than P of A. So what do we know about absolute extreme values? Well, there's a relative min at C if P is defined at C. And again, we're not given that information. We don't know if the derivative here is 0 or if the derivative here is undefined. If the derivative at C is 0, then we have a relative min and an absolute min when x is C. But we don't know that. If the derivative is undefined, we have an asymptote there, it could be that the graph just keeps going down. Okay, so we don't know about absolute minimum. We don't have enough information to tell. But we can now get the absolute maximum. Unlike the other problem, we have a little more information. We know that the endpoint, the left endpoint, is higher up on the graph than the right endpoint. So P has an absolute max at x equals A. Number 43, let S equal 3 times the sine of 2 times t minus pi over 6 plus 5. Find the exact absolute maximum and minimum of S on the provided intervals by testing endpoints and finding and evaluating all relevant critical values of S. So the first thing we're going to do is figure out where we have critical values. S prime is equal to 3 times the cosine of 2 times t minus pi over 6 times the derivative of 2 times t minus pi over 6, which is 2. So I'm going to go ahead and instead of writing times 2 at the end, let's multiply the 2 by the 3 in front to get 6. And then the derivative of the plus 5 is just 0. So where does this equal 0? Well, this equals 0 wherever cosine of 2 times t minus pi over 6 is 0. And that's going to equal 0 whenever 2 times t minus pi over 6 is equal to pi over 2 or 3 pi over 2 plus multiples of pi. Pi over 2 plus multiples of pi, we can say. So pi over 2 plus multiples of pi, where k is an integer. So we're trying to solve this for t. So now we want to divide by 2. So that's when t minus pi over 6 equals pi over 4 plus multiples of pi over 2. And then we're going to add the pi over 6 over to the other side. So t equals pi over 4 plus pi over 6. Pi over 4 plus pi over 6. We can get a common denominator of 12. So that's 5 pi over 12. 5 pi over 12 plus pi over 2k. Now let's look at our intervals and rewrite them in terms of a denominator of 12. So it's easy to see which critical values fall in our intervals. Pi over 6 is the same as 2 pi over 12. And then 7 pi over 6 would be 14 pi over 12. For part B, we're going to have, well, 0 is still just 0. And then pi over 2 is the same as 6 pi over 12. For part C, we've got 0, and then 2 pi is 24 pi over 12. And for part D, 4 pi over 12 to 10 pi over 12. Okay, so I'm going to write critical values of S are going to occur at 5 pi over 12 plus pi over 2 times k. And pi over 2 is the same as 6 pi over 12, so that'll make that a little bit easier as well. So let's keep that over here. And then I'm going to erase this and make some room. So for part A, we're working on the interval from pi over 6, which is 2 pi over 12, to 7 pi over 6, that's 14 pi over 12. So critical values would be, let's just list some of these over here to make this a little bit easier. So we've got 5 pi over 12. The next one is going to be 11 pi over 12. The next one is going to be 17 pi over 12. And then 23 pi over 12. Anything bigger than that is going to be outside of our largest interval. And then we don't have any less than 5 pi over 12 because the next one that would come before that would be negative pi over 12, and all of our intervals start at least at 0. So these are the possible critical values we're working with. So which critical values are between 2 and 14 pi over 12? Well, we've got 5 pi over 12 and 11 pi over 12. And we know our derivative is 0 at each of these values. Actually, I didn't check the endpoints. I cannot assume that. We need a test point between 2 pi over 12 and 5 pi over 12. 4 pi over 12 would be a good one because that reduces to pi over 3. And I erased my derivative equation. Let's put that back up. So S prime, it was 3 times the cosine of 2 times t minus pi over 6, but since we're working in terms of twelfths, I'm going to write 2 pi over 12. And then times the derivative of the inside, which was 2. We multiplied the 2 by the 3 to get 6. So here's the equation we're using to put in our test points. So now we're putting in 4 pi over 12 as a test point. So 4 pi over 12 minus 2 pi over 12 is 2 pi over 12. 2 pi over 12 times 2 is 2 pi over 6. Let me write this down. 2 pi over 12 times 2. Yeah, 4 pi over 12, or pi over 3. Cosine of pi over 3 is positive, and then times 6, positive. Now a test point between 5 pi over 12 and 11 pi over 12, 6 pi over 12 would be a good one there. So 6 pi over 12 minus 2 pi over 12 is 4 pi over 12. 4 pi over 12 is pi over 3 times 2. Cosine of 2 pi over 3, that's quadrant 2, so the cosine is negative. Now test point between 11 pi over 12 and 14 pi over 12, 12 pi over 12 would be a good choice. So 12 pi over 12 minus 2 pi over 12 is 10 pi over 12, or 5 pi over 6. We're going to multiply that by the 2 to get 5 pi over 3. And 5 pi over 3 is quadrant 4. Cosine is positive there. So positive, negative, positive. Now that took a while to figure out just because we had to think about unit circle values. But this is, the derivative equation is just a cosine equation. It's got some transformations applied to it, but it is just a regular cosine equation. So we know it's going to it's going to alternate signs between our critical values, right? It increases, decreases, increases, decreases. There's nothing strange going on with the cosine graph. So once I figure out one of these intervals, I know the rest of them are going to alternate. Now we also know with a cosine function and a sine function, our original s is a sine function, that the maximum value of that sine function is determined by the coefficient in front. So 3 is the amplitude, and we have a vertical shift, right? So even without a calculator, we could sketch out this graph and figure out that its maximum value is 8. because it's shifted up 5, so the sinusoidal axis is at 5, and then the amplitude is 3. So the maximum value is 5 plus 3, or 8, and the minimum value would be 5 minus 3, or 2. So we have a maximum value at 8, minimum value at 2, and all of these relative maxes are going to have the same y-coordinate, and all of our relative mins are going to have the same y-coordinate. What's going to be different about each of these problems, though, is the endpoints, because we're not necessarily ending at a critical value. So we're going to have to check that. If we go back and read the question again, it says, find the exact absolute minimum and maximum of S. That's referring to y-coordinates. So we're not looking to see at what x value do we have our absolute max. It's asking us for the y-coordinates. So I already know if the relative max is the absolute max, then the answer is 8. The absolute max is 8. If the relative min is the absolute min, then the answer is 2. But we have to check our endpoints because, so let's say here's our cosine graph. It's possible the interval they gave us maybe starts right here and ends right here, in which case the absolute minimum value wouldn't be the 2. Although, if this were the case, then we wouldn't see a relative min in our interval. So it's probably a safe bet that since we have a relative max in our interval and we have a relative min in our interval, that the absolute max is 8 and the absolute min is 2. But just to be thorough, let's go ahead and check our endpoints. So S of 2 pi over 12 equals 3 times the sine of, so we're going to do 2 pi over 12 minus pi over 6, and pi over 6 is 2 pi over 12. So that's going to give us 0. So we get the sine of 0, which is 0, times 3, which is still 0, and then plus 5. So that's going to equal 5. Our other endpoint, so S of 14 pi over 12, is 3 times the sine of, so we got 14 pi over 12 minus 2 pi over 12 is 12 pi over 12, or just pi, times 2. It's 2 pi. The sine of 2 pi is 0. Times 3 is 0, plus our 5 is 5. So our absolute max is 8. It's already higher than the 5, and our absolute min is 2. But we can verify that. Let's just verify that for this one problem, and then we don't have to keep doing that for B, C, and D. So S of 5 pi over 12 is going to be 3 times the sine of, so at 5 pi over 12, we have 5 pi over 12 minus 2 pi over 12. That's 3 pi over 12, or pi over 4. Times 2 is pi over 2. The sine of pi over 2 is 1. Times 3 is 3, plus 5 is 8. And then at 11 pi over 12, we have 3 times the sine of 11 pi over 12 minus 2 pi over 12 is 9 pi over 12, times 2 is 9 pi over 6. 9 pi over 6, if we divide top and bottom by 3, is 3 pi over 2. The sine of 3 pi over 2 is negative 1, times 3 is negative 3, plus 5 is 2. So the absolute maximum value is 8, and the absolute minimum value is 2. Part B. Now our interval goes from 0 to pi over 2. Pi over 2 is 6 pi over 12. So what critical values do we have in this interval? Remember, here are our critical values over here. Just the 5 pi over 12. So let's pick a test point of 4 pi over 12. At 4 pi over 12, 4 pi over 12 minus, we're putting it in here, 4 pi over 12 minus 2 pi over 12 is 2 pi over 12 times 2. is 2 pi over 6, which is pi over 3, which is quadrant 1, and cosine is positive. And then I know this one, it alternates on either side of the critical values. So this is going to be positive, and negative is going to give me s increasing and then s decreasing. So at this critical value, I know the maximum is 8. The maximum value of my function is 8. So that's got to be the absolute max. Now, in terms of the absolute min, we didn't get a relative min on this interval. So it's going to be one endpoint or the other. We need to check both of them. S of 0 and S of 6 pi over 12, or pi over 2. Okay, so starting with S of 0, let's go back up here to our sine equation. We have 3 times the sine of, so 0 minus pi over 6 times 2 is negative 2 pi over 6 is negative pi over 3. Negative pi over 3 is quadrant 4, and the sign is negative. So, oh, we need to know the actual value for this one. That's right. Okay, let's start again. 0 minus pi over 6 times 2 is negative pi over 3. The sign of negative pi over 3 is negative root 3 over 2 times 3 plus the 5. So negative 3 root 3 over 2 plus 5. At pi over 2, which is the same as 3 pi over 6, so 3 pi over 6 minus pi over 6 is 2 pi over 6 times 2 is 2 pi over 3. The sign of 2 pi over 3 is positive root 3 over 2. So we have 3 times root 3 over 2 plus 5. And we're looking for the absolute minimum. So this value is smaller. This will be the absolute minimum. 5 minus 3 root 3 over 2. And then our absolute max occurs at 5 pi over 12, and that's going to be the 8. Part C, now our interval goes from 0 to 2 pi. So let's place all of our critical values between 0 and 2 pi on our number line here. We've got 5 pi over 12, 11 pi over 12, 17 pi over 12, and 23 pi over 12. And if we use a test point of 4 pi over 12, we saw that previously, that the derivative is positive, and then we know that we're alternating signs. That doesn't happen in every problem, but we know with our sine and cosine function it is going to happen. So we've got s increasing, decreasing, increasing, decreasing, increasing. So we have relative minimum values of 2, and we have relative maximum values of 8. But we need to know, well, actually we don't need to know what's happening at the endpoints, since we do have maxes and mins in this interval. We know the graph is going to reach a height of 8, and it's not going to reach a height higher than 8. And we know it's going to reach a low point of 2, and it's never going to be less than 2. And again, in this question, they're not asking us for the x values, they're asking us for the y values. Find the maximum, find the minimum. That's talking about the y coordinates. So we can say on this interval we have an absolute max of 8, and we have an absolute min of 2. And for our last interval, now we're working from pi over 3 to 5 pi over 6. So pi over 3 is 4 pi over 12. And then 5 pi over 6 is our 10 pi over 12. critical values. We've got 5 pi over 12. And that's it, because the next one is 11 pi over 12, which is bigger than our endpoint. So between 4 pi over 12 and 5 pi over 12. Let's go with 4.5 pi over 12. We're subbing into our derivative. So 4.5 pi over 12 minus 2 pi over 12 is giving us 2.5 pi over 12 times 2. So 2.5 times 2 is 5. So I've got 5 pi over 12. We're taking the cosine of that and then multiplying it by 6. 5 pi over 12 is still in quadrant 1. So the cosine is positive. And that means this one's going to be negative. This one would be a little easier to check. We can go with 6 pi over 12, which is just pi over 2, or 6 pi over 12. If I go back here, 6 pi over 12 minus 2 pi over 12 is 4 pi over 12, times 2 is 4 pi over 6, which reduces to 2 pi over 3, which is quadrant 2, and their cosine is negative. Okay, so we have S increasing and then decreasing. We have a relative max, and that relative maximum is going to hit a value of 8, so I know that's going to be my absolute maximum value of my function. So we have an absolute max of 8. Now for the min, we don't have any relative mins on our interval, so we need to know what's happening at the endpoints. So I have to find S of 4 pi over 12 and S of 10 pi over 12 and see which one is smaller. So S of 4 pi over 12, we're going back to our equation for S. So 3 times the sine of, I'm putting 4 pi over 12 in for t. And 4 pi over 12 is the same as 2 pi over 6. So 2 pi over 6 minus pi over 6 is pi over 6. Times 2 is pi over 3. The sine of pi over 3 is square root of 3 over 2. So square root of 3 over 2. And then we're adding 5. Okay, so 5 plus 3 root 3 over 2. At 10 pi over 12, 10 pi over 12 is 5 pi over 6. So here, 5 pi over 6 minus pi over 6 is 4 pi over 6 times 2 is 4 pi over 3. 4 pi over 3 is quadrant 3. So sine is negative. So we have 3 times negative square root of 3 over 2. And then plus our 5. So this one is 5 minus 3 root 3 over 2. We're looking for the one that is smaller. So this is the one that is smaller. This is our absolute minimum value, 5 minus 3 root 3 over 2.